Okay. Okay, so in the morning I didn't have time to talk about tensor product, so now it's time. So definition. So let V R be a commutative ring with unity. V and W are not U and V. I like U and V. Are modules, and okay. A tensor product let's go with X okay, tensor product of U and V is an R module X with the following property. The following. Oh, I took the wrong one. Let's change the marker. So for any R module W and any bilinear map. Oh, so let's say phi from U times V to W. There exists a unique linear map. Let's call it phi tilde from X okay, so no, not this way. Maybe no, I will write it in a little bit different way. Only this without the map. So such that L module W such that the space of homomorphisms from X to W is isomorphic to the space of bilinear maps to W. Okay, so in other words, I think the previous marker was better. Yeah. In other words, tensor products represent bilinear maps as linear maps. As linear maps. That's the idea. And this is sometimes called tensor home adjunction. No, not this one, the next one. Okay. And this thing here is also canonical isomorphic to the space of maps. I wrote it, that's the previous lecture, from home U to home VW. And this relation between this is called tensor home adjunction, but not going to discuss that in details. Okay. And there is a theorem that the tensor product is essentially unique. So consider commutative link with unity and two modules, R-Modules. Then there always exists a tensor product of U and W and V, and all tensor products are isomorphic, and all such tensor products are isomorphic. So this is an abstract definition. We don't give explicit construction. We just give what property it should have. And it can be proven that any object with that property, if there exists such, and if you get another one, it is isomorphic to the, if you have y with the same property, then y is isomorphic to S. And we write this abstract object so abstract because it's not uniquely determined. There are some constructions, but the most important thing are the properties of this object. So essentially unique. This is essentially unique. Is denoted by U. So U tensor product with this is multiplication sign in a circle. Sometimes people put this in this subscript R to show what the module over it is. Done. Okay. And so what are the properties of this stick? So the elements of U tensor product with V are linear combinations of terms from the following type. Of the form U small times V small, where U and is in U big and V small is in V big. And it has the following properties. So for now, this is just some kind of notation that doesn't have any meaning now, for now. Okay. And the following identities, the identities hold. So lambda, so if u1, u2 are in U, v1, v2 are in V, lambda, I don't know if I need mu, maybe not, but let's put mu as well. Then, okay, so first of all, if we multiply lambda times U by V, the result is the same as multiplying U by lambda V, and it is lambda a few times V. If we add to U1 plus U2 times V is equal to U1 times V plus U2 tensor product with V. So I said they're linear combinations, so I can form sums, then I can multiply them and so on. There is the other direction. So U times U1 plus V2 plus V2 is equal to U times V1 plus U times V2. Yeah, so maybe I can put here minus as well, but I don't need because I can put it here. So I think this is enough. So we have such abstract objects and we can work using this kind of formulas. If V, U and V are finite dimensional, and we have E is a basis of U, and V, F is a basis of V, then we have that the combination of EYs and FJs is a basis of the product. Then EY times FJ when E is from 1 to M and J is from 1 to N is a basis of U tensor product with V. So what is the dimension of U times U tensor product with V? M times N. So therefore, the dimension of U tensor product with V is the dimension of U times the dimension of V. In this case, it's n times n. Okay. Now tensor products, they behave very well in some sense. So let's just give some example to the example. L2 times L2 or L3, let's say, has a basis the following. So these are real numbers. Let's fix them. 1 0 with 1 0 0, 1 0 with 0 1 0, 1 0 with 0 0 1, and then again the same with the second being 0. So this is a basis of this tensor product. So it's something like 2 by 3 matrices, but they are different than the regular ones, which represent operators. They are distinguished, and I will explain that in a bit. Okay. Now we can also, for instance, space of tuples tensor product with space of matrices. It's not forbidden. We will get something like 3-dimensional objects. So the tensor product has good properties. So let R be a commutative ring with unity, and U, V, and W be arbitrarily the R-modules. Then we have the following canonical isomorphism. We have the following canonical isomorphisms. So canonical isomorphism, let me recall, is something that says that in some way these two units are indistinguishable. They can be interchanged. U tensor product with V is isomorphic to V tensor product with U. So if we get this example and we think of this like 2 by 3 matrices, the other will be 3 by 2 matrices. And in some way they're different, but they're equivalent because they can be mapped to one another. And so to an element of this type is equivalent to an element of this type. We also have U times V times W is canonically isomorphic to U times V times W. So we have associativity. This is like commutativity. They are different spaces, but they're isomorphic. So what do we do here? The obvious one. So U times V times W is equivalent to interchange to it U times V times W. And also U tensor product with R. What do you suggest this is equal to? Okay, but what else? What's the dimension of this thing if this is finite dimension? This is one. So this is itself. So this is isomorphic to U. Like this acts as a unit. So we have U times lambda is interchanged by lambda times U, which is like lambda normal multiplication. Here lambda is a scalar. Okay. And I didn't say, but of course U small is in big Q, V small is in big V, and W small is in W big capital. Okay. Now, these tensor products combine well with home spaces, especially with dual spaces. So let me just give a proposition. So it's better to do it in two steps, but I'll do a single one. Let R be a commutative link with unity, and U, V are R-Modules, and define the following canonical map. How to call it? I thought it and I didn't decide, but let's call it a row. I don't know. A row from. I just want to not from U star times V to the space of linear maps as follows. So when you define a map from the tensor product, as I said, they are linear combinations of things from here and things from here. But usually you just give the how it maps a single how it's called atomic tensor. So atomic tensor is when there is no sum, there is only this something from here multiplied by something from here as false. So for any f in U star, so f is from U to R linear. and V2 in V and U small in U big, we have the following. So rho, we start with F times V. So this is an element of U star times V product. And then we have to define a linear map. So to define a linear map, we have to show how it acts on vectors of U. So this thing here, when acting on U, is given by F of U times V. So this is a scalar. This is scalar multiplication. And this thing, this map, if U is R or V is R or both are two-dimensional or finite dimensional, sorry, or both U and V are finite dimensional, then rho is an isomorphism. I think there are examples when one is two-dimensional, the other is infinite dimensional that don't work. But if this is one-dimensional U or V is one-dimensional or both are finite dimensional, then we are fine. So this tells that if we have a linear map from U to V, we can decompose it as a linear map from U to the real numbers and then take the V parts separately. Okay, so this gives the following like corollary that physicists love to use. I mean, in mathematicians as well. So because when physicists talk about tensors and maps, they usually don't talk about those spaces and functions. They only talk about tensor products of covariant and contravariant vectors. So they of course work for real numbers, but it can be generalized. Be a commutative link with unity, and V is finite dimensional. I mean, theoretical physicists usually use this kind of knowledge. R-Modules. Then any vectors, any R-module constructed out of V, those places, V, maybe R, okay, dual modules, tensor products, and home sets, home spaces. So home spaces are listed here. Home spaces is isomorphic to V So I didn't define, but I will define it. M tensor power of M of V times N tensor power of V star for some V M and natural. Here, tensor power N of V is V times V times V, N times. I don't put brackets because from associativity, we can distract them. So if you start with a finite dimensional space and make this kind of operations, you cannot get out of here. I will not write a formal proof, but the idea is assume you have such a module. And if you tensor product with module of this type, their indices of the contravariant parts will add and the indices of the covariant parts will add. If you take the dual of this will be the tensor product of M of V star n times multiplied by this double stars will become no star, become V. So the indices interchange. And if you make a home of this and something like that, when you use this kind of identification, because we proved it's closed under tensor products, it's closed under double joules. When you combine, it's again closed. So these are the only tensors that you work with. And in physics, they love to work with indices. They give a very long formulas for how to change indices in bases. Here, we work with abstract vector space, abstract modules or abstract vector spaces, and we don't need any indices, but we need a little bit more theory. Okay. Also, side note, I didn't write, but I thought maybe I should put it. If you and we are, this is a side note, right? Another identity are finite dimensional, then U times V star is isomorphic to U star tensor product with V star. Sorry, this is star. Okay. There is tensor product of linear maps. I'm not going to use it, I think, so I will not define, but if we have two linear maps, we can combine them as a single linear map from the tensor product of the inputs to the tensor product of the outputs. Okay, now let's go to direct sums. This is usually easier, but I want to do the multiplicative part first, and now I do direct sums. Why I need direct sums? Because I want to introduce tensor algebras, and particularly the exterior algebra, which are sums of spaces of different, like different dimensions, but different structure in some sense, in different essence. So now let's go direct sums. So let R be an R module. Sorry, our commutative link with unity, and VW, U and V maybe, are modules. And here I will give concrete definition. And we define U direct product with V to be this time here. So with pointwise operation, with pointwise operation. So we separately do operations on the first and on the second. So if we have, so if U1, U2, V1 are in U, and maybe U small. V1, V1, V2 are in V, and lambda is in R, then we have the following. So, and the elements, of U plus V are denoted by small, the same symbol, but with elements. U plus V, where U is in U and V is in V. I had to put this here, but anyway. Then so lambda times U plus V is lambda times U plus lambda times V. U1, U2 plus V1, V2. Sorry. No. Sorry. U1 plus V1, and we add this. So this addition is in the product. So it's in product. U2 plus V2 is U1 plus U2. This is in U. Direct sum in U plus V by V1 plus V2. This operation is in V. If we wrote comma inside instead of components, this will be adding the first component and the second component separately. And yeah, so let me write this proposition. This is very simple one. What do you think the dimension of the direct sum is? Of two things. So let R be a commutative ring with unity, U, V are finite dimensional. R-Modules. Then, okay, so if E is a basis of U, F is a basis of V, then we have the following. So E1 plus 0, which we write is just a E1 plus 0, En plus 0. And then we swap the vector. So E0 plus F1, 0 plus Fn. This thing here is a basis of U plus V. And so what's the dimension? Yeah. Therefore, and so hence, the dimension of U direct sum with V is dimension of U plus dimension of V, which is M plus N. Okay. So, for example, if we have let's give R plus R2 some simple example is the same as R3. How? Well, if we have so E1 is 1 and basis of R. F1 is 1, 0, basis of sorry, they're both. F1, F2 is 0, 1. These both are basis of R squared. Okay, and then what we do? So we have 1 plus 0. This is the 0 vector here. And then we have 0 plus 1, 0. And 0 plus 0, 1 is a basis of this thing here. So this is a basis of R plus R squared. Okay, but if I remove these pluses and change with brackets and go outside, which equivalent to the basis 1 0 0 0 1 0 0 0 1 of R third. So 1 0 0 0 1 0 0 0 1. This is, sorry, this should be this kind of plus with circle. Okay. And now, again, there are some identifications that we can do. So let's write them down. So let UVW is enough, okay. RB and R module. I always forget about commutative link with unity and think about module. So U, V, W are R modules. Then we have the following canonical isomorphisms. This is very bad. Okay, so this is also, maybe I should write, is there another black here? Okay, so U plus V, what do you think is? V plus U. How do I identify them? So I have a pair here, what I mapped it. V plus U. Yeah. We have associativity as well. U plus V plus W. I always put the first bracket differently, but doesn't matter. U plus V plus W here, and U plus V plus W is the same as U plus V, this with W. Okay. What is the identity element here? What should we add to get the same space? The zero vector space equal to U. Again, U plus, the only element of the zero vector space is the zero vector. So this is the same as 0 plus U, which is the same as U. We also have U. These things work for any kind of U star plus V star. How do I do that? So if I have F plus G, so if F plus G in this thing here, we should map it to a single map. So we map it to the map to the element that H in U plus V star H of. How do you suggest what H of U plus V should be? So I have this map and have to map to something here. How to, so F is some element of U star, G is some element of V star. So what should I do? How to expand this using F and G? No. I have F function element of U star, G element of V star. And I want to make it an element of U plus V star. So that means it's a function from U plus V to R. How to, so I need to get a relationship between F plus G and H, yes?
U plus U.
Yes. So that's in R, and that is in R. And the whole result is in R. This is R. And we have the associative property, not associative, distributive. So U plus V tensor product with W. So remember, if the dimension of this is M, this is N, this is P, is M plus N times P, which is the same as M times P plus V times N times P. Now, what's the identification here? So if I have U plus V times W, what should I map to?
U times W plus V times.
Yeah, so this is W. So U times W plus V times W. Okay. And I have the opposite direction. Because this was commutative, but I will write it down. U tensor product with V plus W is the same as U times V plus U times W. And again, so U, this is identified by U times V plus U times W. Yes, okay. What time is it? Okay, let's make a break.